Swayam Prabha. Digital India. Educated India.
So what we are going to do now is we are going to study something that's completely graph theoretic, right? So the material is presented out of the text by Douglas West. And this is a chapter on matchings and covers. It's not the whole chapter, but just a initial part of it. Right? So the goal of this chapter is to introduce these two graph theoretic concepts and prove a few theorems. And as usual, I'll point out things that you can actually convert into an algorithm at many of the places when we try to write these proofs. And for all the discussions, we will be working with undirected graphs here. Right? So what we have is a graph G with vertex set V and edge set E. A matching, as we have probably discussed a bit earlier, is a set of vertex disjoint edges. Right? So, for example, a single edge is a matching. Therefore, the natural question to ask is find a maximum cardinality matching. Or rather, one should not really worry too much about find. Right? So, we are interested in the set of all matchings, and in particular, we are interested in the set of matchings which have a maximum number of edges. Right? Because if the graph is non-empty, right, so then anyway you have a matching of minimum cardinality, which is very well understood, right? Just a single edge. Right? So let us just look at the set of all maximum matchings. Right? So every maximum matching is actually a special kind of a matching called a maximal matching. Right? A maximal matching is one. Right? By maximal we mean inclusion maximal. And by maximum we mean cardinality maximal. Right? So maximal with respect to cardinality means there is no matching of larger size. Right? Maximal matching is inclusion maximal, which means that the current matching is not a subset of any other matching. Right? So let's do a small example just to see the difference between a maximal matching and a maximum matching. So let's look at this graph and let's consider the matching, which is let us consider M1 to be the matching which consists of the edges AB and EF. Let's consider the matching M2 which has the edges AC, BD and EF. right? You can already notice that the first one is not a maximum matching, but it is maximal, meaning that you cannot add one more edge from the graph, right, and get a larger matching. Let us just see this, right? So I've added AB, this is in the matching, right, and this is in the matching. So obviously I cannot increase the size of this matching by adding one more edge, right, because the edges in a matching have to be vertex disjoint. So therefore this is an inclusion maximal matching, but obviously the matching is of the maximum cardinality matching has more edges in it. So this leads to the most natural question, right? For that, let's go back to our example and try and see how to make the first maximal matching a larger matching. Right? What will definitely fail is if you try to add an edge, because there is no such edge, right? So let me just draw the picture again. Right? So now let's write the matching down, right? So this is AC, right, and EF. It's a maximal matching, but let us look at the maximum matching which we have. The yeah, it's AB, right, and EF, right. So this is a maximal matching. Now let's see what are the edges which are missing, and let's try to represent them in an interesting way. Right? So let us look at the maximum cardinality matching, which is AC, BD, right, and EF. Right. So what you would have already observed is that if you take M1 union M2, right, to understand the structure of maximum matchings, right, if you have a maximal matching and if you have a maximum matching, consider the union of M1 and M2, right. So the union of M1 and M2 can be thought of as the edges which are common to both of them and the edges in the symmetric difference of the two of them. Fine, okay. So let us write down the guys which are common. Let's put a oval around them. These two are common, right? And let's look at the symmetric difference. And let us draw the graph which is formed by the edges in the symmetric difference, right? So this is AB, there is AC, and there is B, right? So what you now see is the C is an unmatched vertex in M1 and D is an unmatched vertex in M1, right? And you now have the possibility of doing an exchange, right, in matching M1. So what is the exchange? Remove this from the matching and add these two. In other words, you are augmenting the matching by using a special kind of a substructure, right? We'll name the substructure shortly, and you are getting a larger matching. Fine. So note that in this example, I will define an augmenting path shortly, but you can just focus on the English definition, right. So, the matching M1, right, by some approach can be augmented and you will get a larger matching. And what is the approach? The approach is to take this particular path CA, right, where C is unmatched in M1, this is very important, A is matched in M1, B is matched in M1 and D is unmatched in M1 and DB is an edge, right. So, observe that this immediately allows you to perform a switch saying that I will discard this and I will discard this and I will add these two. Right. Such a path that enables you to change is called an augmenting path. We will formalize that in a minute. So, we introduce this concept of an augmenting path for a matching M. Right. We say that first of all it must be a path P. Right. By definition of a path, it is essentially a sequence of vertices and edges. Let us call this V1, E1, V2, E2, V3, right, Vk, Ek and Vk plus 1. An augmenting path first of all is a path, right, as per the usual graph theoretic definition. Right. Second one, V1 and Vk plus 1 are the only unmatched vertices So, if you look at the vertices of this path P and you ask which are the vertices which are not matched in the matching M, there are only two of them and they are V1 and Vk plus 1. Every other vertex is matched, right. 3. All the other vertices are matched. E2 is in M. Right. Well, I should have started off by saying because V1 is unmatched, okay, quite obviously E1 is not in M, right, because V1 is unmatched. In an augmenting path P, E2 is in M, E3 is not in M, E4 is in M, right. The matching edge and the edge from outside the matching occur alternatingly, right. So, in other words, the picture will look like this: dotted line not in the matching, dark line in the matching, dotted line not in the matching, dark line in the matching, dotted line, dark line, and what will it end with? So, what can you say about Ek? Quite obviously it is not, it is a dotted line, it is not in the matching. Now, as you can see, you can do a neat exchange using this path, change the matching, right, by adding Ek to the matching, adding E1 to the matching, removing E2 from the matching, adding E3 into the matching, and so on, finally adding Ek into the matching and removing Ek minus 1, right. So, observe that This has resulted in the increase in the size of the matching. There are two more vertices which were unmatched, which have now got matched, right? And therefore the matching size has increased. And every other vertex which was matched continues to remain matched. Fine. So therefore this is a complete definition of a augmenting path P for a matching. First of all, it must be a path P. Second of all, with respect to the matching, you will find that the first and the last vertex are unmatched in the matching, and inside this match, the odd numbered edges, right, are not in the matching, and the even numbered edges are in the matching, right? 1, 3, 5, etc., etc., right? 2, 4, 6, 8 are in the matching, right? So as you can see, 1, 3, and so on, right, are not in the matching, whereas 2, 4, and so on are obviously in the matching, right? And doubtlessly there are an even number of vertices in this path which I did not mention, right? So k plus 1, vk plus 1 is a even number, because at the end of this, all the edges of this path, right, all the vertices on this path are matched, therefore there must obviously be an even number of vertices, right? All right. Therefore, what do we know? We know that if you have a matching and you want to increase the size of the matching, here is the algorithmic question. Does this matching have an augmenting path? By the way, I didn't mention this. When you talk about an augmenting path for a particular matching, you call it a M augmenting path, right? So that there is no ambiguity when we discuss. It's just a terminology, right? So this M and this M are one and the same. Fine. So any ideas how to go about it? Any thoughts? I mean, the reason I'm asking you is that you can use your graph traversal techniques that you have studied so far to check if there is a path. Now I'm asking you to think about whether, using your graph traversal techniques in a slightly modified way, you can check if there is a path which is an M augmenting path. Meaning that there's a path where the matching and the edges outside the matching are going to occur alternatingly. So let me try to show you this, right? So it's going to be a modification of a BFS kind of a traversal, right? So what am I going to do? I'm going to start at U, an unmatched vertex. Well, you may ask me, how do you know an unmatched vertex exists, right? If there is no unmatched vertex, then the augmenting path is a maximum. Sorry, the matching is a maximum because every vertex is matched, right? And that's the best situation. Fine. So therefore, you can look for an unmatched vertex, right, and start a following kind of a traversal at the unmatched vertex. Because it is an unmatched vertex, all the edges incident on it, right, are edges which are not in the matching. Fine. Now let us assume that I find a vertex V, right, which is not in the matching, which is unmatched. So let's assume that one neighbor is unmatched. Have you found an augmenting path? So one possibility is that you explore the neighbors of U, inspect each neighbor, and you ask, is this matched by M? If it turns out that this V is unmatched by M, my question to you is, have you found a M augmenting path? Yes, it is an M augmenting path. Yes, while you say that VU can be added, you are right. That's a consequence of applying the definition correctly. If you look at the definition of an M augmenting path, you must have a path starting and ending at unmatched vertices, and the intermediate edges alternate between matching edges and edges outside the matching. And obviously this single edge satisfies all the desired properties. So therefore, yes, you found a M augmenting path, right? So therefore, you've answered yes. So when can you not answer yes? It turns out that each of the neighbors, right, is in the matching, right? Each of the neighbors is matched, and this edge is the edge which is in the matching. Is this clear? So the algorithm continues. Now what do? You go here. This is the only edge obviously in the matching. Therefore, the remaining edges which are incident on it are not in the matching, because in the matching the edges have to be vertex disjoint. So these edges are obviously not in the matching. Right? Now there are only two possibilities. You look at this vertex. Let us call this V prime. Either it is unmatched, right? That is, it's not matched by any edge in the matching, in which case this path is an M augmenting path, right? Otherwise, it will turn out that this guy is matched. Therefore, by this modified, as you can see, it has a kind of a breadth-first search kind of a flavor, where the layers alternate between layers where the vertices are matched and the layers where the edges are not in the matching. So in this layer, none of the edges are in the matching. In this layer, all the edges are in the matching if the algorithm has to proceed, right? So therefore, layer after layer you will explore the graph, right? There are only two ways of terminating. Either you will find an alternating path, or you will conclude, either you will find an augmenting path, or you will conclude that for this unmatched vertex, I cannot find an augmenting path. I cannot find an augmenting path which starts at this particular vertex U. Fine. So what was the question? The question is, does there exist an M augmenting path? So what do? Iterate over all unmatched vertices. Right? So you have a matching, and you've now concluded that either you can increase the size of the matching by this procedure, right, or you can conclude that you can't increase the size of the matching at all by this procedure. What is the procedure? Start at an unmatched vertex, do this BFS kind of layered exploration. It will terminate either by finding an augmenting path, or you will conclude that this modified BFS exploration cannot lead to a M augmenting path. In which case you try the next unmatched vertex. If you fail for all unmatched vertices, then you say that I have not been able to find a M augmenting path for this particular matching. Fine. So therefore, this algorithm, I leave the analysis of the running time of this algorithm as an exercise to you. Fine. Clearly it's polynomial time, right, because it's like a modified BFS, right, but just completely write down the best possible analysis. But now the question is that, are augmenting paths the only way of increasing the size of the matching? Let's ask the question down. So we've answered this question, we've given a polynomial time algorithm, right, and let's continue with our graph theoretic thread. Right. We've seen that if M has an augmenting path, we can find a larger matching in G. Natural question, right? If you can't find what can you conclude? If you cannot find an augmenting path, then what can you conclude? Yeah, we will now conclude that M is a maximum matching. Fine. And indeed, we will now write a proof of this claim, right? That M is a maximum matching if and only if there is an M augmenting path. That's what we are going to prove now. Fine. So let us just write this. Right? One direction is done. If M has an M augmenting path, then you can increase the size of the matching. Right? Now let's assume that M does not have an M augmenting path. I am going to argue that none of you can ever find a larger matching in the graph. Fine. So let us write this down. Let M not have an augmenting path. Right. Now let's do a proof by contradiction here. Let M prime be a matching such that cardinality of M prime is more than cardinality of M. It has one more edge, which means M prime matches two more vertices than M. Fine. So the same trick that we did earlier, consider M union M prime, break it into the edges which are common to M and M prime and the edges which are in the symmetric difference. Right. Now let us observe some nice properties here. Right. What can you say about the graph formed by the edges only in the symmetric difference? So let me put this question down. Before that, let's observe one small thing. This implies that M is maximal. This I forgot to say, meaning that you can't add one more edge to M. Otherwise, that would have been an augmenting path. Fine. So M is a maximal matching. M prime is a maximum matching. Right. M prime has at least one more edge than M. Right. And we are trying to understand the structure of the edges which are in the symmetric difference of the two matchings. So what properties can you observe? Let's start off with the simplest of them. Right. Fine. Yeah. Okay. Great. Right. So the simplest one, which he's already answered. Right, he's given a stronger answer, but let me point out the simplest of ones. Degree of each vertex is what? Less than or equal to 2. It's either 0, 1 or 2. Right? Because both of them are matchings. Right? Which means that every vertex either has an edge incident on it which is in the matching or it does not have. It could be, the degree could be 2 because the vertex is matched in both the matchings, right? Or it's matched exactly in one of the two, or it's matched in neither. in which case its degree will be 0. Right? Therefore, what is the property of such a graph in which every vertex has degree 0, 1 or 2? So, it basically looks like this. Single vertices maybe, or maybe some paths, right, or some cycles. Degree would be more than 2. Right? Fine. So, it cannot be a non-trivial tree. I mean, it can only be a path. Right? It cannot be any other tree, because then that would mean a degree of at least 3, but because you are taking the union of 2 matchings. Right? Okay. Now, let us focus. Right? So, is such a cycle possible, by the way? I deliberately drew it. Right? So, maybe this edge is in the first matching. Right? Then this vertex is matched to this edge, right? This vertex via this edge in the second matching. So, 1, 2, right? Then obviously this vertex could not be matched to this, right? So, this vertex is matched to this vertex by this edge in the first matching only, not in the second matching, right? And so on. So, how long can these cycles be? Yes, right. So, obviously the cycles cannot be of odd length at all, right. So, if you look at every cycle, it is a even cycle, fine. Okay. Similarly, if you look at a path which is there, the edges will alternate between the 2 matchings. So, it will be in the first matching, this will be the second matching, and this will be in the first matching. Right? Of course, it is quite possible that it could end at the second matching also. Fine. Okay. So, now what do we know? We know that M prime has even number of vertices, M has even number of vertices, right, and M prime has more vertices than M. When you take out the common vertices and look at them, right, so you will now see that the symmetric difference is now a union of paths and cycles, and obviously even length cycles. Fine. Okay. So, even length cycles are not going to give us any handle. What am I trying to show? I am trying to show that M must have an augmenting path. That is my goal, right. By looking at the even length cycles, you are not going to get an augmenting path. Exchanging them is going to give you, an exchange of the same cardinality, right. So, now we focus only on the paths.